Welcome to this video, and in this video I want to have a look at how to derive the Hill sphere equation. So what is the Hill sphere equation? Well, the Hill sphere or the Hill radius or the sphere of influence is basically an area in the shape of a sphere around an astronomical body, and it's the region in which it would dominate the gravitational attraction of smaller objects. So if an object is within the Hill sphere of another astronomical object, then it will be dominated by its gravitational attraction. So for example, for the Earth, the Moon has to have an orbit that lies inside the Hill sphere of Earth. So typically what you find is that moons will always be within the Hill sphere of the planet. And the same is actually true for planets around a star. So planets will be orbiting a star and they will be in the Hill sphere of that particular star. And it scales basically with mass and the distances between them. So what we're going to do is we're going to find an expression for that, an equation, which will help us work out exactly where it would be. So first, let's have two masses. So in this case here, I'll just use the Sun and Jupiter. So the larger mass is going to be the Sun, the smaller mass is going to be Jupiter. And then there is a semi-major axis, which is basically the orbital distance of the planet. So the distance between the two. If it's a circular orbit, then the distance between the two will always be the same, and it will be this semi-major axis. But it's basically their separation. So we've got those three variables then. We're then going to call the Hill radius or Hill sphere R Hill. So again, this is the radius of that sphere around the second smaller mass. In this case here, I've just used Jupiter. So what we're going to do is we'll place a small third test particle on an orbit at the Hill radius. Now, when we say a test particle, this is a very, very small mass, which is almost negligible in mass. So maybe in this case here, a spacecraft would probably work. It's so small in comparison to all the other objects here that it's essentially negligible in mass. So that's what we mean by a test particle. So we're going to place that on an orbit at the Hill radius. Now, we don't know what the Hill radius is yet, but by doing so, we can work it out. So when it's on a orbit at the Hill radius, we can then draw a line between the large and the smaller mass, and that test particle will be in between the two, and the distance from the smaller mass will be the Hill radius, and the distance from the larger mass will be the semi-major axis minus the Hill radius. Now what we're going to do here is we're going to balance the gravitational and centrifugal forces acting on that test particle, and it will act in a line, and then we can find an expression for the Hill radius. So we need to balance those forces basically. So this is the starting point. So in the yellow we've got the gravitational force acting on the test particle from the smaller mass. The green is then the gravitational force from the larger mass, and obviously they're in different directions because they're in a line and one's pulling that way, one's pulling the other way. And then the blue is the angular velocity of the smaller mass as it orbits around the larger one. So we basically have the angular velocity and the gravitational forces here, and they then balance out to equal 0. So here we can actually rewrite the omega as the Keplerian angular velocity, which is a function of the larger mass and the semi-major axis. So the bigger the mass, then the faster the orbital velocity needs to be, and the further away it is, then the slower it would be. So we can basically use that, put it into our equation. Once we do that, then we divide by g, because then the g's can come out. So we're starting to get there. But we can also rewrite it in this form here. So what we've done there is on the first bracket we brought out a 1 over a squared, which is the semi-major axis, and then the second bracket we basically just brought out an a. So it's reduced that a cubed to a squared. So it's just a bit more convenient to write like that. And then on the first bracket we can do a binomial expansion, make some approximation there, and write it in the form at the bottom there. So we've removed that to the -2 for the bracket and brought it inside the bracket and written it in that form there. So then we can basically bring those two brackets together and make an approximation. So we can approximate that to be 0, and it basically simplifies it a little bit. So in this case here, we brought those together and we've got 3 times the hill radius over the semi-major axis instead of having the 2 brackets at the top there. So now what we can do is we can basically multiply out the brackets and then we can equate them together. So we now have 3m, the hill radius, over a cubed, and that equals then the smaller mass over the hill radius squared, because we can equate those now because it's approximately equal to 0, which means they must cancel out. So now we can then divide both sides by 3m, because we want to basically move everything over to one side and just leave the hill radius on the other. So we do that, which basically means we now left with the hill radius divided by the semi-major axis cubed on the right hand side. So we need to kind of get that a cubed over to the other side. So then we can multiply both sides by the a cubed, and that will then leave us with the hill radius on one side and then the rest of it on the other side. However, there's still a hill radius on both sides of the equation, so we have a 1 over the hill radius squared on the left hand side, so we need to bring that back over again, and we'll end up with the hill radius cubed basically. So now we just bring that, well, we multiply both sides by the hill radius squared, and then we end up with this expression here. So that, from there, it's quite straightforward then to get our expression or approximation for the hill radius. We just take the cube root basically. So then, taking the cube root, we get this approximation for the hill radius, hill sphere, or sphere of influence. So it's basically going to be the semi-major axis times the cube root of the smaller mass divided by 3 times the larger mass. So it should be fairly obvious to look at this, that it's going to depend on the distance between the two objects as well as their relative masses. So if they're separated by quite a distance, then the hill radius will be larger. If we have a look at things like the planets in our solar system, the planets, as they get further out, will have a larger hill radius because their semi-major axis increases. And the same is true for the mass. So if the smaller mass, the planet mass, is bigger, they will have a bigger hill sphere. If they have a smaller mass, they'll have a smaller hill sphere, and if the larger of the two masses is bigger in comparison to the smaller one, then again you get a smaller hill radius. So it's about the relative masses and their distances between them. But, I mean, that's an approximation for a circular orbit of the planet. We're assuming a planet anyway. If it's on an elliptical orbit, so it has some eccentricity, which is denoted as E in the above equation, then you need to use that version there. So what happens there is, because it's on an elliptical orbit, it will move closer and then further away, and it changes the hill radius. So you then have to reduce the hill radius because it becomes more unstable. So an orbit would have to be a lot further into the hill radius to remain stable. But that is how we get the hill radius. So thank you for watching, and if you enjoy, you can check out some of the other videos.